Good morning and good afternoon. This is Monica Paolini from Senza Fili. Today I'm talking to Philip Sorrells, the Vice President of Strategic Marketing at CommScope. And this is a conversation that it's part of a report on RAN optimization and how this is changing with networks becoming more complex and more dynamic. And Philip will tell us more about what he's doing at CommScope in this area. Philip, thanks for being with us today.
Thank you, Monica. It's a great pleasure to be with you today.
So to get started, can you tell us what you're doing at CommScope?
Well, CommScope is doing a lot of things right now. So we are actively involved. Of course, our mission really in life is to provide broadband connectivity solutions to the wireless market, the telecom market, and enterprise customers all over the world, bringing connected and efficient solutions with fiber, copper solutions, and of course our air interface solutions that comes out of the Andrew brand of CommScope solutions.
And specifically in the RAN optimization, what is it?
Well, the RAN optimization is a huge topic. It's a big topic for our wireless customers, and clearly, as you know, in our Andrew wireless division, our core competency there is the RF path. So this is an area that we spend a lot of time really working on the RF path, and we've got some really key initiatives that we've developed over the last 3, 4, 5 years, even a little bit longer, all aimed at helping the mobile operator community optimize their RAN. And there's, I'd say, 3 big picture areas. One we call sector sculpting, another we call sector splitting, and a third that is more along the lines of kind of in the design phase, how do you optimize the performance of the antenna system with beam tilting and beam management.
Mm-hmm. Now, before we get into the sort of the more detailed part, can you tell me how, you've been doing this for a very long time. So how has the RAN optimization changed over the years? What is new that we have to do today that we didn't have to do a few years ago, or that we didn't do a few years ago?
That's an outstanding question. And I don't want to give a lot of history lessons, but I think some of it's relative and very important. Let's keep in mind that in the 80s and 90s, we had 2G technology that was really designed for voice. And so the design parameters of that network had different KPIs that were more important for a design for voice technology than other characteristics. 3G was designed for voice with consideration for data, a pretty big consideration, but still the primary tool, the primary output goal was still voice. 4G is a completely different animal. 4G is designed for data, and voice is a part of that, right? So voice is now considered a part of a data package in 4G. So the network design parameters are different. The KPIs, for example, a very good example. In 2G, a key KPI out of the antenna system was ultimate gain. How much gain you could get out of the antenna system and coverage. In LTE, which is an interference limited system, the primary KPI is SINR. How much noise and interference you can reduce between sectors. 2 very different parameters, and they create all types of different challenges for RAN optimization.
Right, and so this is really it's a qualitative difference. It's not you have to do more, you have to do things differently. And so let's get started on how the new RAN optimization platform is. So the first one you mentioned was a sector sculpting.
Right. So sector sculpting is a term that we use to try to describe the techniques that are applied to shape the energy as it comes out of the face of the antenna. Right. So the energy doesn't just blob out in space. It really is architected to come out with the goal, especially in LTE, the goal of putting that energy only in the sector that you want it. So there's some fairly distinctive characteristics. For example, in 2G, it was relatively okay to have a large amount of overlap between one sector and the next. In 3G, we wanted to start to minimize that overlap to reduce soft handoffs. And in LTE, an interference limited system, ideally, we would have virtually no overlap at all. The sector edge would be completely clean, and we would have very, very little overlap of energy. So sector sculpting is all about how to design antenna systems so that we shape all of the 360-degree balloon that is, in fact, the antenna. So there's two primary planes. There's the horizontal plane and the elevation plane, and they both have characteristics that need careful shaping for ultimate performance.
Is this also related to the different patterns of frequency reuse?
Absolutely. So a good example is one very important antenna characteristic in an LTE network as well as a 3G network is the front to back ratio. So the front to back ratio defines the energy being emitted behind the antenna compared to the energy that's being emitted in front of the antenna. Well, if you have poor front to back ratio, then that energy can actually interfere with other antennas on your sector, or there could be another antenna system, another cell site that could interfere into your cell site because of poor backlobe suppression. That's a factor called front to back. It's one of the techniques that it's an area that we really have specialized over the year, try to design antenna systems that have what I call a very well-behaved front to back ratio.
Yeah. And that's crucial because spectrum is so expensive. You want to take as
much,
absolutely. You want to squeeze as much as possible out of it.
Absolutely.
Okay. So the next one, so you first make sure that you have your sectors tight.
Right.
The next one is the beam splitting. What do you do there?
Well, so again, a little bit of a history lesson. Way back in the beginning, cell sites were omnidirectional, 360-degree sector. The next logical thing was to split that to 3 sectors. So we took an omni, we split that to 3. And if you go look at networks today, the vast majority of cell sites are actually 3-sector cell sites. There's an evolution beyond that that we call 6 sectors. And fundamentally, the idea there is take the a nominal 65-degree per sector site, take those sectors, split those into 2 different beams. Now you add more radio resources. The new beams are nominal 35-degree beams. So together they still cover that 65-degree area. But each one of those now has more gain. The gain goes up as the horizontal beam width goes down. So the gain goes up. And the beams are more precise, so you have less interference between sectors. So you get 2 nice hits with one upgrade of your equipment. You get more gain, improving the signal strength in the S-sin R equation, and you reduce interference. So it really is a great way to take a cell site or even a sector that's particularly loaded and get a nice shot of capacity and optimization into that sector. Mm-hmm. Now, beyond that, we're working on technologies like we have, for example, a 5-beam antenna that's used in really super hot spots. Imagine, for example, in Japan, there's one very famous area in Japan where there's 3 big subways that kind of dump off into one area. So at any given time, there's thousands of people there. You can imagine they all want to use their mobile device all at the same time. So in that particular area, they have our 5-beam antenna solution that just penetrates that landing area and provides really fantastic quality and service for those customers in that location.
Mm-hmm. So operators really seem to like the 6 sector, but a few years back, you thought, well, 3 sectors is really all you want to do. Are we going to be heading to more than 6 sectors?
Well, there certainly are discussions of even a 9 sector. So you may have read recently that we have released a technology for what we call a 3-beam antenna. So now instead of having 2 beams out of one antenna face, you now have 3 beams out of one antenna face. That type of antenna technology can be used, fantastic application for super hot spots. So if you've got one sector that's fully loaded and you need to do something dramatic to increase the capacity of that sector, this 3-beam antenna is a great tool for that. But when you take the whole cell site and convert it from 3 sectors to 9 sectors, you have the possibility, operators have the possibility of making a really dramatic improvement in their network optimization in terms of capacity throughput.
Now, does this mean that if you increase a lot of if you make the macro cells more powerful, have more capacity, does that delay the need for small cells? Because this has already happened to some extent. Operators are moving from 3 sectors to 6 sectors, and hence they have less of a need for a small cell type of deployment. Do you think that it's going to work out that way?
Well, certainly on the outside world, it will. It makes common sense that if you've already invested hundreds of thousands or even millions of dollars for the physical location where a macro cell is, it makes common sense that you would do everything you can to optimize the capacity out of that investment before you make a future investment, especially in the outdoor world. So techniques like this, going to a 6 sector or 3 beams or even 5 beams on a sector, or doing some other advanced techniques, can extend the useful economic and technical life of the macro and push back, in some cases, not all cases, but in some cases, it can push back when an additional layer of small cells is needed for certainly an outdoor ecosystem.
Mm-hmm. Right. And that sort of makes sense, because this is what we have been seeing already, that the operators are trying to optimize the macro as much as they can. So,
Absolutely.
and so another way to do it, another way to optimize the RAN is beam steering. What are you doing in that area?
Well, CommScope, originally in our Andrew portfolio, we actually were the developers of the technology for remote electrical down tilting. So when we look at, in terms of RAN optimization, there's a lot of different dials and buttons that the network engineering community have to improve the performance of the network. They can do power adjustments, they can do neighbor list adjustments of which frequencies are used. So there's a lot of dials and buttons they can use, but one of the most powerful ones is optimization of the beam pointing direction of the antenna system. And that's important because if you imagine 2 cell sites that are facing each other, if they have no beam tilt, it's very possible that these beams could create interference. So a common technique and a very important technique is the ability to move this beam here, move this beam here, and reduce the area of overlap. Certainly with our beam tilting apparatus, our remote electrical tilt apparatus, that function is now used in virtually all LTE deployments, not all, but close to all, and is seen as one of the most important buttons to push to optimize the performance of the network. So today, that technology can be used remotely. You can set in the knock and see where there's interference and make tilt adjustments remotely. You can also go to the cell site and use a little controller at the cell site without having to climb the tower. So that technique is very well established and a very powerful part of RAN optimization.
Now, these adjustments, are they? Do you tend to do them on a frequent basis based on what you're seeing in terms of usage, or is it something that it's just a minor tweak that you do rarely?
Today, our observation is that the capability is there to do really frequent adjustments. So that capability is there. It can be fed with SON, self-optimizing network algorithms that many different companies in the industry are promoting and providing to the network operators for usage and for trials. So the capability is to do that in pretty much real time exists. But our observation is that that doesn't really happen. What really happens is more human time. Imagine, again, if you will, with me, that if you walk into virtually any network operators' engineering offices, virtually anywhere in the world, they'll have a conference room and they'll have either a map or a display that shows every sector they have that they're responsible for. And that sector will have a red or a green. And if it's a red, that basically means that the interference level at that sector is below a certain threshold of KPIs that really gives them the best overall performance of the network. And that team of engineers are firing off every day to try to figure out which knobs to hit to get that red to turn green. This ability to do down tilting is one of those knobs, and it's used quite frequently when they see sectors in a cluster that have a characteristics that say if you adjust this one and adjust this one, you can make an impact.
And then, yeah, okay. So, and now when with the introduction of small cells, which is not that many out there now, but there is an increasing number of small cells and multi-layer topologies out there, the need for optimization becomes even more prominent, but also more complex, because especially if you have co-channel deployments, you need to manage interference even in a more aggressive way. You have to be much more careful about interference because you are transmitting the same area, same frequency. How is that going to work out?
Well, I think there's a lot of techniques that are being deployed in LTEA. There's certainly some interference mitigation software algorithms that are used to help identify that and avoid it. In the RAN design and RAN optimization routines, they can simulate where these small cells are and how much energy is around those small cells and what needs to be done to avoid interference with a macro, and they can do some beam tilting on that as well. So there's a lot of different techniques that are really kind of existing techniques. It's just now you have a smaller cell site with lower power that creates a little bit different problem, but the fundamental techniques are still the same.
Now, what about carrier aggregation, where you have to optimize across different frequencies at the same time?
Certainly, carrier aggregation is evolving to become a really important tool. I still personally want to give that a little time to see how it evolves and is really used before I can really talk with a lot of confidence about how it fits into network optimization, RAN optimization, at least in terms of what we're doing in the RF path. But you bring up an interesting point, which is all the new frequencies that are being out there. And those frequencies obviously are a crucial element of the operator's RAN optimization strategy. But just like everything good, it also has some bad. Those frequencies now mix to create different kinds of interference, right? So we add a new band, and we find that band then has a interference mode with this radio. So you may have operator A stepping on operator B's receivers, or operator B stepping on operator C's transceiver. So there's all kinds of things that happen then, and there's also the topic of passive intermods, where you have different frequencies now that can mix and create passive intermods, which is a pretty big challenge for LTE networks in particular. One of the things that we're trying to do there is we have a line of what we call interference mitigation filters, where our filter design team will come in and do an evaluation of the frequency bands that are being deployed in these clusters and the new frequency bands that are coming in, and looking at where the possible interference overlaps are, and then designing kind of custom filters to put a little pad to make sure that we don't really, that those interference problems don't eat away at the capacity that we just purchased with this acquisition of new capacity.
Yeah, yeah, yeah. So, in closing, what are you working on next, and what are the next challenges that we have to meet in optimizing the RAN performance?
Well, I think there's a couple areas. Clearly, the continuation of the conversation of how we exploit all the indoor space is a big conversation. You know, if you think about it, at least on the commercial enterprise world, there's something like 30 billion square meters of enterprise space that needs mobility that doesn't have mobility today. Well, as an RF guy, I see that as real estate. Right? I see that as real estate that I can put in cell sites. And hey, building capacity in networks is all about densification, and you got to have real estate to densify. So there's all this real estate available for densification, but we've got to get the right mix of technologies into those enterprise building locations. So that, to me, continues to be a big frontier of where the technology will continue to evolve, probably for another 2 or 3 years. And then the last one that I think is interesting and is, you know, for many years now, we've talked about the het net, and the het net being the macro layer and a small cell layer. And it's starting to really gel in my mind that's really kind of an incomplete picture. It's not really 2 layers. I think it probably is more like 4 layers. The macro layer, what I would call the metro layer, which are still outdoor cell sites, but much lower antenna height, perhaps significantly lower power, but still maybe 5 watts, maybe 10 watts, but lower antenna heights, kind of nestle into the urban area outdoor space. And then what we think of as the small cell layer for outdoor space, you know, really super hot spots, and then this whole in-building thing. And I think that then when you add in what happens with the Internet of Things, and we go from hundreds of millions of connected people with their mobile device to billions of connected things, you know, when people say there's billions of connected things, I see billions of potential sources of interference as an RF guy, right? I say, wow, that's billions of interference points. So I think that whole technology evolution of how we continue to push forward with adding more and more densification, adding more and more devices, and then ultimately we still have to look at the basic fundamentals of good quality RF. You got to have good signal strength, and you got to have interference mitigation. And those techniques for getting that to the market at the right time, that's what we're thinking about today.
Yeah, and I think it's a very interesting perspective you have in terms of not being too different, you know, the 2 different extremes. There's just going to be so much more. And that really allows us to optimize depending on what you're trying to do. It's not, you don't optimize in a vacuum, you optimize for a purpose. And as you say, the Internet of Things is gonna change all of that. So, well, with that, I would like to thank you so much for taking the time to talk to us and share your insight on this today.
You're more than welcome. It was a pleasure.
So I was talking today to Philip Sorrells, VP of Strategic Marketing at CommScope, and this was for a report I'm writing on RAN optimization in collaboration with RCR Wireless. The report is available from the websites to download, and I would like to thank you very much for watching this.